So you have 30 minutes over. Probably good not to go over at least 10 minutes. So anyway, I'll let you.
Oh yeah.
So this is Xailong, and Xailong is currently a master's student at UCLA working with Ron, and is now going to tell us about how to design liquidity-sensitive market makers. Take it away.
Okay. So, yeah, Jake already introduced us. So, our topic is designing automatic market makers with adaptive liquidity. So basically, we are trying to explore the duality-based framework and try to find what kind of market maker have adaptive liquidity. So first, some background definition, because I think some of them are already covered in the previous talk, so I will go over it very quickly. So a security market offers a set of securities with payoff linked to the future states of the world. A prediction market is a special kind of security market that is created for the purpose of making predictions, and the current market prices can be interpreted as prediction of the probability of the future events. And here is some example. So let's see a more realistic example. I just screenshot from the InTrade, which is a large website for betting prediction market. The topic of this market is Barack Obama to be re-elected president in 2012. And the rule of this market, it says on the website, is that the market settles at $10 if the named individual is re-elected in 2012 and $0 otherwise. So we can see how the market price corresponds to the estimated chance you can see in the top right corner there. So basically, you can calculate the expected payoff of the security given that chance, which is actually a measure of the value of the security, and it is exactly $5.27, which is the current market price. By convention, so in our following discussion, we will also always assume that security always pay $1. So in that case, the market price can be directly interpreted as an estimated belief. So here is a chart about the price variation of this market in the past 1.5 years. You can see there's a lot of trading going on here, and the price is varied a lot. Implies that the underlying belief of this event actually changes over time. So here's another screenshot showing all the unmatched prediction in the market. So you can see that there's a lot of unmatched orders, and the bid-offer spread, which is actually the difference between the highest buying price and lowest selling price, is only 1 cent, which means the market is very active and trade is very likely to go on. However, due to the nature of prediction market, this is not always the case. Because actually, we will say a market is a thin market if there are relatively less activities. And actually, most of the market from InTrade are actually thin market. So here is a very typical example from InTrade. The title is Rock of Ages, a movie by Tom Cruise to cross over some amount of money in the open weekend. And one can see that there's only one purchase order with only 10 cents and only 2 shares. There's a lot of selling order though, but the minimum selling price is $2. And it seems to us that the trade are not going to happen here. And another problem that you can see there are more than on the right column, more than 600 shares have been sold under the price $2.60, which means there is a very stronger belief in the crowd that this event should not happen with a probability higher than 26%. However, the estimated chance is still 32.5%, that's shown on the top right corner, which means that the information from the traders are not reflected in the market in a timely fashion, which is another problem for a thin market. So how to solve this kind of problem? It is well known that the introduction of a market maker will do the job. So a market maker is basically a company or an individual that codes both a buy and a sell price. So we will focus basically on the market maker-based markets. So we need to know what's the goals for market makers. The first goal is pricing the market, as by the definition. And the market maker needs to provide liquidity to the market. and preferably varying the liquidity level according to the activity level of the market. So I remember Ralph says that he will prefer the market liquidity to like increase over time so that the market can converge. So this is also some of our consideration. And because market maker take some risk, so he always want to avoid unbounded loss, and preferably we want the market maker to make a profit. It can be shown that when the market is satisfying certain condition called path independence, then it can be solely determined by a cost function. So we will focus on cost function-based market makers. A cost function is a potential function C defined on the R to the n. The argument of this function is the number of shares of each security sold to the traders. And I refer it to market states. I think someone agree with that because once the cost function is fixed, this quantity Q completely determines the behavior and property of the market currently. The value of the function is the total amount of money accumulated in the market. So if the current market state is Q and the trader wants to buy a bundle R, where a bundle R is a vector of n component, meaning numbers of each security a trader wants to buy, then he pays the difference of the cost function, which is, and it should be noticed that when the cost function is differentiable, then its differential or its gradient defines the current instantaneous price, which we denote as P of Q. So basically, I want to introduce 3 frameworks for designing cost function-based market makers. The first one is duality-based market makers by Abernathy, Chen, Wang. Actually, the first paper appeared in 2011. The second is what they call the homogeneous risk measures by Altman and Sandholm in 2011. And in the end, we'll talk about our framework, which we call the liquidity adaptive market makers. So we'll first discuss about the first existing frameworks, and then to talk about what we think the problem is and what motivates for our new framework. For the duality-based market makers, they first propose several conditions that they think desirable for a market maker, namely information incorporation, arbitrage, bounded loss, and expressiveness. I think I'm not going to extend what the exact meaning of this, but most of them are very explicit from the name. And their main result is that for any market satisfying those conditions, the cost function can be and must be defined as the following convex optimization problem. And this is a maximization over a probability syntax about dot product minus some strictly convex function R, which in convex analysis is called the conjugate dual of the cost function. And I will call the probability syntax, which is a feasible set in this optimization, the price space. The reason is that it can be shown that the instantaneous price when the cost function is differentiable is actually the maximizer of this objective function. So the price is always taken from the feasible set. So that's why I call it the price space. So let's to discuss the property of duality-based market makers, let's review what we want a market maker to achieve. So here are the goals. So basically, duality-based market maker satisfying all the goals in the black font, but not in the red ones. But particularly, the duality-based market maker is liquidity insensitive, which we'll define in the next slide. And although it has unbounded loss, it cannot make a guaranteed profit. Actually, if the event happens where most amount of the security is sold, then duality-based market maker will always lose or draw even. So why liquidity insensitivity is not desirable? First of all, market liquidity is defined as an asset's ability to be sold without causing a significant movement in the price and with minimum loss values. So for loss function, it basically means the price P of Q changes slowly with the market state Q. Then we say the market has high liquidity and vice versa. In 2010, Altman defined the market to be liquidity insensitive if for any market state Q and any scalar alpha, the price and market state Q is the same as the price, and market state Q plus alpha 1, where the body 1 is a vector of all ones. So why this is undesirable? So here is a more realistic example. Suppose we have two securities in the market. So P of XY represent the prices when X shares of the first securities and Y shares of the second securities are sold. And then by the definition of liquidity and sensitivity, we will have this equation holds. The left-hand side intuitively seem to be a very strong bias towards the first outcome because 100 share of the first security are sold, but none for the second security. While the right-hand side seems to be quite the same confidence in both the outcomes by the market. So this intuitively seems that the price in these two cases shouldn't be the same. And there are actually other justifications for whether liquidity insensitivity is undesirable, but this is most simple one. So why duality-based market cannot make a profit? So a very simple idea is that because the sum of prices is always 1, because the price space is the probability syntax itself, and there is always some outcome that will cause the market maker not to gain money. Actually, the outcome corresponding to the largest number of securities sold. I think to actually trying to solve these two problems, the homogeneous risk measures are proposed, which is another class of cost functions defined in this way, a maximization about merely a dot product over price space Y, which is strictly convex and compact. And it's obvious that this definition gives you a homogeneous function, which means when you scale the argument, you scale the value of the function by the same scale. And it is shown in their paper that homogeneous risk measures is not liquidity insensitive, and it is profitable. So I'm not going to prove why this is true, but an intuition is to deviate the price space from the syntax. Consider we have two securities, and this axis means the prices of each of the securities. The price space for the duality-based market is the probability syntax here. While in homogeneous risk measure, they made it something like this arc segment thing we denoted by Y. So there's two differences. First of all, the probability syntax is only some subset of a flat subspace, while our new price space Y has some curvature. Actually, we show that it is the curvature of the price space that guarantees the liquidity sensitivity. Another thing to notice is that the new price space Y is entirely above the probability syntax, which means the prices always sum up to more than 1. And this is actually the source for the profit. It seems that homogeneous risk measure is a perfect solution by not having all the 5 goals we want for a market maker to achieve. But we notice two problems. The first one is that we think homogeneity is not really necessary for liquidity sensitivity. And we want to explore a larger set of functions, or even the entire class of cost functions that are liquidity sensitive. Another thing is that we believe that liquidity sensitivity and profitability does not come without any cost. There must be other aspects of the market that are sacrificed, and we want to find a trade-off between them. In order to find the entire class that have a liquidity sensitive property, we first make a stronger definition about what we want the liquidity to be. So basically, we'll define a cost function to be liquidity adaptive, just another synonym to distinguish from liquidity sensitivity for our new definition. If for any purchase bundle R in the positive quotient, the price change after buying that bundle goes to 0 when the market state goes to infinity. This actually means when the market runs market states goes to infinity, the liquidity goes to infinity as well. The reason why we didn't define it using the hasten of C goes to 0 is because we don't require the cost function to be twice differentiable. In this definition, it only need to be once differentiable. As a comparison, so this is what we just saw, the definition for liquidity insensitivity. And it can be shown that liquidity adaptation implies liquidity sensitivity, but not vice versa. That's why we say R is a stronger notation. One thing to notice that we allow only buying in the market, as seen by our definition, because we only consider all the R in the positive order. The reason is that we want to make a profit by making the prices sum up to more than one. If we allow selling in these circumstances, the trader can always sell the same amount of each securities and always gain from the market maker, and we have unbounded loss. And there are other justifications for this constraints as well. Our main result, which I'm kind of cheating here because just to make it simple. So this is a little bit different from what we have in the paper, but the main idea is the same. So any buy-only market with certain desired property, namely information incorporation, no buy-only arbitrage, bounded loss, and liquidity adaptation, most importantly, can be and must be defined as an optimization problem in this form, which is a maximization over a dot product minus a strictly convex and bounded conjugate on the strictly convex and compact set. And I think you should probably notice that this is actually a combination of the previous two frameworks, essentially. And basically, we inherited the generality from the duality-based market by keeping the conjugate term R, but we require it to be bounded just to prove some of the properties. And we inherited the advantages of homogeneous risk measure by not limiting the market, the price space to the probability simplex. So to measure the trade-off, we want to first have a more theoretical definition for profitability. So actually we define asymptotic profit rate, which in plain words is the worst case profit rate when the market runs long enough, in a long term. The worst case means worst case against the worst possible outcome and the worst possible final market states. So the denominator here is just the amount of money accumulated in the market. We kind of decompose the final market states as a scalar length lambda times a direction vector q. And the numerator here is the amount of money accumulated in the market minus the worst case amount of money you have to pay for the traders. And the maximization and the inf taken here actually means the worst case. And the limit taking lambda to infinity means we want the market to run long enough. So this is why we call it asymptotic profit rate. It's an asymptotic behavior of the market. So we prove that we can actually calculate this profit rate rho by a formula that is only related by the determined by the shape of the price space. And it can be shown that this profit rate always positive if the prices always sum up to more than one. So here's a more like illustration of this. So basically, we calculate B is larger than 1, which is actually, in this case, the minimum sum of price. And by the previous formula, we can calculate that rho is 1 minus 1 over something bigger than 1, so it's positive, which means that for this market, the market maker is guaranteed to make a profit, a linear profit in long term, and the coefficient is rho. Okay.
This profit guarantee is only if they buy, like, in some sense, balanced, right? If they only buy both assets.
No,
Traders only buy one asset.
You can do that. Because
and you're charging them more than one.
Yeah, you cannot buy. It's not reasonable for you to buy only one asset. Yeah, but you have a belief. You can still reflect your belief here. But you cannot buy only one asset. Yeah. So this is kind of guaranteed profitability. Yeah, no matter what the final state is.
You said that capital Y had to be strictly convex.
Yeah, so I'm a little bit cheating here because we are only consider the positive direction. So it should be strictly convex on all the positive direction. So the negative direction is okay. Yeah, so basically we define what we call the positive boundary as this curve there. And it must be nonlinear. But yeah, the negative direction or other direction are okay, actually.
But yeah, just to make sure I'm understanding correctly. So it doesn't, wouldn't it be reasonable to have it, to require that on the edges, the price does not go above 1?
Yeah, you can actually take an intersection of the y here and the unit hypercube. And you take the intersection as a new price space, which sounds more reasonable. And because they're all convex, so their intersection is still convex. Yeah, you can do that. But basically, to make it simpler, we just let it go off. But in reality, any sane people will never reach some point in this.
Yeah.
So you can actually take an intersection, but all the results are the same.
No, but the guaranteed profitability is not, right?
You still, for example, if you take a, yeah.
We can talk about it.
Just cut it off.
Yeah. I think you will still, yeah. For example, if you take an intersection of this with the unit hypercube, then actually you rule out the 0.01. So you can never do that anymore. Yeah, that's it. Okay, so as we said, we believe there must be some other aspect of the market that is sacrificed, and it is expressiveness. We define a market as buy-only expressive if for any market state Q in the positive orthant, and for any belief B, there exists some purchase bundle R in the positive orthant such that by purchasing this bundle R, a trader can set the price to his belief. This is very important because we said the prediction market is specifically created for the purpose of making predictions. And it's very important for the market maker to have the ability to interpret the market price as a trader's belief. However, we prove that a market cannot be simultaneously expressive and liquidity adaptive. So are we hopeless because we cannot exactly recover the trader's belief anymore? But the answer is no. So although we cannot know exactly what the trader's belief is, we can still limit to some range. So that means we have lost some information, but not all of them. To measure how much information we have lost, we define the belief set B given the market state Q as a set of beliefs with which a myopic risk-neutral trader will not trade. So in our case, it can be shown that the belief set is all the probabilities component-wisely upper bounded by the current market price. So that is very intuitive because, for example, if a trader has some belief that is higher than current market price, then he always wants to buy that security and always have some positive expected payoff if he's risk neutral. For example, if the prices sum up to exactly 1, then the belief set is a single point, which means that we have not lost any information. However, if the prices sum up to more than 1, then the belief set is not a single point. And we measure our lost information by the size of the belief set, which we define by the 1 norm diameter of this set. Another very important result we get is that we bounded this information loss. We give a bound to this information loss, and which has a very nice interpretation. So basically, we first assume that there is some minimum purchase unit epsilon as in any real market because you cannot buy half a share in a stock market, and so on. We also assume that the cost function is twice differentiable, but this is not really essential, but make things simpler. So basically, we bound the information loss by 2 terms. The first term we call is a hard information loss, actually measures how much your price space deviates from the probability syntax. As you can see, it's 2 times maximum sum of price minus 1. The second term we call the soft information loss is due to the inability to trade arbitrarily small unit. So it is controlled by the minimum purchase unit, the number of securities, and also the lambda max of the hasten of C, which measures the instantaneous liquidity. Because we define a market to be liquidity adaptive only if its liquidity goes to infinity when the market state goes to infinity. So basically, the soft information loss will finally diminish as the market runs long enough. So within this bound and our profitability definition, we can now get a trade-off. Basically, we have shown that the profitabilities, so here in the graph, B is the minimum sum of price and A is the maximum sum of price on the horizontal axis. So basically, we have shown before that profit rate is calculated in this way. So we want B to be larger to get a large profit rate. We also showed in previous slide that hard information loss is related to the maximum sum of price, and we want A to be smaller. We want the maximum sum price to be smaller. We also showed that the higher the liquidity, the smaller self-information loss. What we haven't shown in the slide, but we prove in the paper, is that actually the liquidity is related to the curvature of Y, and larger curvature of Y gives higher liquidity, which means we want larger curvature of Y in order to get smaller self-information loss. So basically, there are 3 goals for us in the blue font, which are actually conflicting each other from the graph. Right? We want B to be larger, A to be smaller, while we want the price space to be more curvier. So how to leverage these trade-offs? We showed that we first fix A and B, which means we first fix the profit rate and hard information loss bound. Then we show that the price space Y of the optimal market, in the sense that minimize the self-information loss, must have the bound of a Euclidean bound. And the center bound is not necessary at the origin. And this is our final result. So as a conclusion, we first found a large set of cost function-based market makers that have adapted liquidity and are profitable in the long term. Then we define information loss, which is the cost we have to pay for liquidity adaptation and profitability. And in the end, we discuss the trade-off among liquidity, profitability, and information loss. And that's all. Okay, thank you.
I suggest we let the questions happen during the coffee break, which is now, since we only have about 20 minutes, or barely more than 50 minutes. So I guess we'll meet here back at 4 o'clock. Feel free to ask Xailong questions. Do you guys have it?